Okay. Let's welcome Yeshwant Pandit for his talk on EF1.
Good afternoon, everyone, and welcome. So I'll be talking about EF1 allocations for identical ternary valuations. This is joint work with Umang Bhaskar, Gunjan Kumar, and Varshita. So this problem has gathered significant attention from the researchers who are working at the intersection of computer science and economics, and which is why we are also motivated to study this problem. Okay, so in a fair division problem, we are given a set of indivisible items. So what do you mean by an indivisible item? So an item cannot be divided and distributed among agents. It has to be given either completely to some agent or it is left unassigned. We have a set of agents who have values for these items. Okay, and there is a central panel whose task is to fairly allocate items among the agents. So what it means for an allocation to be fair, we'll see that shortly. So formally, we are given a set M of indivisible items, a set N of agents. Each agent I has a valuation function, which takes us input a subset and spits out an integer value. So we can also assume that it spits out a real value, but for this talk, we'll assume that it gives out an integer value. So an allocation is an in partition of the set of items M, and the goal is to fairly allocate these items among the agents.
In partition means that every item is allocated.
Exactly. So we're looking for a complete allocation.
But if there is an item which has negative valuation, for example, which everybody values negative, then
We will see that. We will see that. So yeah. So what are the fairness notions? So how do we measure fairness? So there are different fairness notions that have been studied in the literature. Envy-freeness, equitability, proportionality. So our focus will be on envy-freeness in this talk. Okay. So to answer your question, so items can be of different kinds. Like we have goods and chores. So before that, let me define what is called marginal value. So marginal value of an item X with respect to a set S for an agent I is just Vi of S union X minus V of S. So what does this mean? Like what gain or loss do you get after adding item X to subset S? Okay. So if the gain is positive, that means if by adding X to S, if the value of the resulting bundle increases, then we say it is a good. Otherwise, we say it is a chore. Okay. I mean, if the value is negative, we say it is a chore. So here is an example of a good. So this agent values milk at 15, and if it's given flakes along with milk, then he values it at 25. So there is a positive marginal value for flakes. So an item is a chore if the marginal value for an item is negative. Okay, so in this case, if waffle is added to milk, then this person values it at a lesser value. Okay. And we say that an item is irrelevant when it has marginal value 0. Okay. That means this doesn't change the bundle value if he adds banana to this. Okay.
Is it additive?
We'll see different valuation functions here. Okay, so this will answer your question. So there are different valuation functions studied in the literature. So these are the common encountered ones. So a function is valuation function is edited if the value of the subset is just the sum of the values of the individual items present in it. Okay. We say that our valuation function is monotone non-decreasing if for any two subsets S and T, we have where S is a subset of T, we say V of S is greater than or equal to V of T. Okay. So we also refer to this as monotone goods. Okay. Similarly, we have monotone chores where we require that the condition should be V of S should be less than or equal to V of T. Okay. So this can contain items with positive. This can contain items with positive marginals and 0 marginals. This can contain items with negative marginals and 0 marginals. Okay. So there is something called as doubly monotone valuation, where each agent I partitions the set M of items into two sets, GI and CI, where GI is a set of goods for it and CI is a set of chores for it. Okay. And agent I has arbitrary monotone non-decreasing valuation over its goods and arbitrary monotone non-decreasing valuation over its chores. Okay. So coming back to envy-freeness, which is the fairness notion we're going to study in this in this talk. So an allocation A is envy-free if each agent prefers his bundle to any other agent's bundle. Normally, for any pair of agents, VI AI should be greater than or equal to VI AI. So let's just understand this by means of an example. So the allocation that is highlighted in orange is EF. So where agent 1 gets item G1, agent 2 gets item G2, items G2 and G3. Agent 1 has valuation 20 for its bundle. It has valuation 10 for agent 2's bundle. So agent is happy with his bundle, agent 1. And agent 2 values its bundle at 25, whereas it values agent 1's bundle at 10. So it is also happy with it. So this is an envy-free allocation. On the other hand, if you see this allocation, the green allocation where agent 1 gets G2, G3 and agent 2 gets G1, agent 1 envies agent 2 because agent 1 has value 10 for its bundle and it values agent 2's bundle at 20. So I forgot to mention that we are assuming additive valuations in this example. Okay. So envy-freeness may not exist. Envy-free allocations may not always exist. You just even if you have a single item and two agents who are value it positively. Okay. So this motivates us to look at its relaxations. So one of the relaxations that is studied in the literature is envy-freeness up to one item. So what it says, you are allowed to envy in an allocation, but by removing some item from either your bundle or the envied agent's bundle, okay, the envy should get eliminated. Okay. So in this example, the orange allocation is EF1. White is EF1. Let us check. So agent 1 has item G1, agent 2 has, so this example is an example of doubly monotone valuation. So, okay, where agent 1 has a set of goods and it has a chore, and agent 2 has a set of goods and this is a chore. Okay. So agent 1 has value 20 for its bundle. So agent 1 doesn't envy agent 2. Okay. Whereas agent 2 envies agent 1. Okay. But this envy can be eliminated by removing this chore. Okay. However, this this cannot be. I'm sorry. If you remove, so let's just concentrate on the green allocation. So green allocation is EF1, so where agent 1 gets item G2 and it gets chore C1. Agent 2 gets item G1. Okay. So agent 1 envies agent 2. However, removing this chore, the envy gets eliminated. Removing good G1, the envy gets eliminated. Okay. But this orange allocation is not EF1. Okay. If you see that removing good G1 and even chore C1, the envy between agent 2 and agent 1 is not getting eliminated. Okay. So do EF1 allocations always exist? So this is a prior work on the existence of EF1 allocations. So for monotone goods, we know that EF1 allocations always exist and it can be obtained via envy cycle elimination algorithm. So this result is due to Lipton and others. For doubly monotone, with the additional condition that the valuations are additive, the existence of EF1 allocation is guaranteed by the double round robin algorithm. Okay, and this result was extended by Bhaskar et al. And they showed that EF1 allocation always exists for doubly monotone valuations by suitably modifying this envy cycle elimination algorithm. Okay, this is a recent work which shows that EF1 allocation exists for the following cases. That is when we have two agents, when the instances has two agents and their valuations are arbitrary. When agents' valuations are binary, okay, that is any agent values any subset. It has. For any subset, any agent has value either 0 or 1. Okay, so we call them as positive binary. And when agents' valuations are identical and negative binary, that is V of S. So agents are identical, so we can drop the subscript here. So V of S can take either value 0 or -1. So we try to extend the
So if
results.
any one of the following conditions for EF1 allocations.
No, for all these cases, EF1 allocation.
Yeah, anyone.
Oh, sorry.
Yeah.
Okay, so these are our results. So for negative binary, so this was for identical negative binary. Okay, and we showed that for negative binary, that means for any agent, any subset is valued either 0 or -1. Okay, we showed the existence of EF1 allocations. And for identical and negative ternary, that means where a subset can take either of these three values, like 0, 1, or -1, or it can take either 0, 1, or 2. So in these cases, we have shown that EF1 allocations always exist. So our focus will be on the first two results. So the plan is to cover approve first two results. Okay. So for that, we need some notation. So for an agent I and a subset S of items, we define the following. So Vi of S is equal to A right arrow B, which says that S has, so agent I has value A for S, and by removing some item, that is item X, S of S minus X is valued at 2. Okay. So Vi of S is A, and there exists some element in S, by removing which the resulting subset is valued at 2. Okay. So, this notation says, like Vi of S is A double right arrow B, which says that by removing any item, okay, the values of the resulting subset should be B. S has value A for agent I, and S minus X1, S minus X2, and so on, they have value B for agent I. Okay, and this is just an extension of these notations. Okay. So now we'll show the result for negative binary valuations. So what's the intuition for the algorithm? So observe that an allocation is not EF1 if and only if we have two agents, I and J, such that agent I values its bundle at -1, and by removing any item, the resulting bundle has value -1 for it. Okay. Whereas it values agent J's bundle at 0, and by removing any item from agent J's bundle, the resulting subset has value 0 for it. Okay. So how do we overcome this problem? So this is a rough intuition. Like we repeatedly select an inclusion-wise minimal subset with value -1 for all unallocated agents, and we assign that subset to that agent. Okay. So what do we mean by inclusion-wise minimal subset that has value -1? Let us see. Okay. So let M prime be the set of unallocated items currently. Okay. And agent I1, I2 up to IN prime are the agents that are currently being unallocated. I mean, they haven't received any benefits till now. Okay, all these agents. So if any one of the remaining agents value n prime at 0, we simply go and assign that subset n prime to it. Okay. So we assume that all the agents value n prime at -1. Okay. So M prime is a set of unallocated agents. So I'm saying that S is an inclusion-wise minimal subset which has value -1 for all agents. That means no proper subset of it. Okay, no proper subset of it will have value -1 for all the agents. So for example, if you take S prime, it has value -1 for agent I1, but for agent 2, it has value 0. Okay. So we look for such subset S, which is valued -1 by all the agents, all the remaining agents, and it is inclusion-wise minimal. So that no proper subset of it will have value -1 for all the agents. Okay, with this, what do we get? So for example, in case of agent I2, we can assign set S to agent I2, Okay, why? Because agent I2 will, it values its subset at -1, but by removing some item, it knows that, okay, its value can become 0.
So in this allocation process, you are fixing an order over item.
Yeah, so so in this allocation process, whoever gets a bundle first, it will be like, so the sequence of the agents would be the sequence in which the items are allocated, the bundles are allocated. So initially, so I'll show the algorithm. So initially you start with an empty allocation. M prime is a set of unallocated items. N prime is a set of unallocated agents, the agents who haven't received any bundles yet. M prime is the set of items that are currently not being allocated. Okay, so as long as M prime is non-empty and we have two agents, and all the agents in this set of remaining agents, all these agents are valued M prime at -1. Okay, that is what we want, right? Okay. Then you find an inclusion-wise minimal set, okay, such that it is valued by some, that is valued -1 by all the agents. Okay, we assign this subset S, okay, to an agent, okay. So we assign this subset to an agent I, okay, such that by removing some item, its value is 0. And we have already seen that, right? That such a subset can, such a subset we can assign to agent I. So the question that we should ask is, does this set always exist? Okay. So the answer is yes, because all the agents value M prime at -1. Okay, and all the empty sets are valued at 0. So this is an assumption which I missed. Okay, so all the empty sets are valued at 0. Okay, so what you can do is you can start with M prime. Okay, it is valued at -1 by all the agents. Look at the children of M prime, which are the subsets that are obtained by removing a single item from it. Okay, if you get some subset which is valued 0 by some agent, okay, you just assign M prime to it. Otherwise, you recurse down the tree. Okay, so the existence of such a subset is guaranteed. Okay, so we assign such a subset. Okay, in the loop. So when do we come out of the loop? If for all the agents, M prime is not valued at -1, that means there is some agent who values M prime at 0. Okay, so in that case, you assign M prime to that agent. Okay, and the last condition is when we have no items remaining or we have only single agent remaining, you just assign the remaining subset to it. Okay, so we'll see now where this algorithm gives us an EF1 allocation. So assume that agents 1 to k are the agents who received bundles inside the loop. Consider any agent I that has been allocated inside the loop. Okay, we won't care about the agents who have received bundles after k. Okay, so the agents are reindexed so that 1, 2, 3 up to n is a sequence in which the agents have received the bundles. Okay, so after k, all the agents have received bundles such that their value is 0. So they won't envy anyone. So we just have to be concerned about the agents who receive bundles inside the loop. So consider any agent I in the loop. Okay, and consider any agent j who has been allocated a bundle before I. So by the allocation process, A has received a bundle which was minimal, inclusion-wise minimal, and it had value -1 for all. I mean, for all means for all the agents who appeared after J. Okay, so VI of AJ is -1. So agent I values agent J's bundle at -1. Okay, so agent I won't envy agent J. Okay, so I doesn't envy agent J. Now, what if agent J appears after I? Okay, so I could envy J. Okay, but we have the guarantee that agent I received a minimal inclusion-wise minimal subset such that its value is -1, and by removing some item, its value becomes 0. So agent I may envy agent J, but that envy can be removed by removing some item from its bundle. Okay. Hence, the allocation that is obtained after running this algorithm is here. Okay. So how much time do I have? 6 minutes. 6 minutes, okay. So let's just look at the existence of identical negative ternary valuations. Okay. So here we draw the subscript because the valuations are identical. So subsets are they take values from this set, 0, 1 or -1. Okay, so at any point of in our algorithm, okay, that we propose for this identical negative ternary case, each agent belongs to one or more sets. Okay, so these are the sets. So set is unallocated. An agent belongs to this set of set which is denoted by U called unallocated set. If it receives an empty bundle, okay, it belongs to 0 if it may receive a non-empty bundle, but the value for that bundle is 0. Okay, so favorable set contains all those agents who value their bundle at 1, and by removing some item, they value their bundle, the resulting bundle at -1. Okay, similarly, they value that bundle at -1, and by removing some item, the resulting bundle is valued at 1. So these are the sets that we look for. So we can blindly assign the sets, right? Because if you assign the set to some agent, okay, the other agent may envy this guy. Since the valuations are identical, some other agent, let's say J, has same value for AI. Okay, so it may envy this guy. But we know that by removing some item X, the envy would get eliminated because AI minus X is -1. Okay. Similarly, if you assign this to some agent I, then agent I may envy some other agent. But we know that there exists some element X by removing which we get a bundle that is valued at 1. So even if there is an envy from I towards some other agent, that can be eliminated. And if there is an envy from some other agent towards I, that can be eliminated. So favorable sets are the sets which we can go and blindly assign to the agents. Okay. Then we have something called as flexible. So flexible sets are the sets which say agent I has value 0, and by removing some item, the resulting bundle is valued at 1, and similarly it has value 0 for the bundle, and by removing some item, it has value -1. Okay, so after assigning favorable sets, we go and assign flexible sets. I'll show you how do we do that. First, let us look at this definitions. So result bundle is a bundle where agent I has value 1 for its bundle, and by removing some item, the resulting bundle is having value 0. And similarly, we have -1 and 0. So this is a bad bundle. So when an agent belongs to this set, either bad plus or bad minus, this is something which we need to worry about. Okay, because removing any item from this, okay, so it has value 1, and by removing any item, the resulting subset also has value 1. Okay, and similarly, okay. So let us look at the possible EF1 violations that we can have. Okay, so whenever we have favorable set, we just go and assign those favorable sets. Okay, right. So I'll highlight all the possible EF1 violations here, but the green, the edges that are highlighted in green are the violations that we encounter in our algorithm. Okay, other violations we do not encounter. Okay, so as long as we have favorable sets, we go ahead and assign them. Okay, then we go ahead and assign the flexible sets. Okay, and after which we go ahead and assign the sets, the bundles that are resolved. Okay, so at the end we may get a violation from a flexible set to a bundle which is in bad plus. Okay, because here the value for the bundle is 0, and by removing some item, the value is -1. We could have, by removing any item, we could have the value 0 or -1. So in that case, an agent who gets a bundle from this set may envy this guy, and then that envy is not EF1. Okay. So this is another possible violation that we can have. So the other ones, right, the black ones are the EF1 violations that we don't encounter in our lab. Okay. So almost one. Okay. So yeah, so I'll just show you how the allocations look like. Just stop me whenever. So it's all okay. Okay. So I'll jump to the open questions. Yeah, so these are the open questions. So we don't know whether EF1 allocations always exist for non-identical ternary valuations. In fact, even for identical KR evaluations, this question is unanswered. So in general, you want to know what are the boundaries of valuations for which EF1 allocations always exist, and can we make this algorithm very efficient? So the algorithm which we gave for negative binary is polynomial time algorithm, but for the identical case, we don't know how to do it.
They allocate 1 minute to you, no one will tell you.
Okay, so yeah, thanks for your attention.
So, what exactly is the difference between positive binary and negative binary?
So yeah, so when I say positive binary, that means any subset can take value either 0 or 1. When I say
Subset, the entire subset has
the entire subset has value either 0 or 1, and negative binary means the entire subset has value either 0 or minus,
not the individual axis.
not the individual. So we are looking for any arbitrary valuations. We are going beyond monotone, we are beyond doubly-monotone.
Any other words?